Hello listeners and viewers. Welcome to Kaduna State Ministry of Education Radio and TV e-learning program designed for our SS3 and other students staying at home due to the coronavirus pandemic. The present administration, under the able leadership of His Excellency, Malam Nasir Ahmed El-Rufai, is positioned as always to ensure that under his leadership, our students are not left behind in all areas of human endeavors, especially education. Kaduna State is the center of learning. Therefore, we want to ensure that our students excel in their forthcoming examinations and beyond. Students and other learners at home are given this opportunity in order to continue learning, as education is a continuous process. Different subjects will be taught in this program to assist students to perform excellently in the forthcoming Senior School Certificate examination being conducted by NECO and WAEC as soon as schools reopen. Teachers making presentations will always provide their names and phone numbers during each presentation, and they can be contacted for questions, further explanations, and/or clarifications. The following numbers and contacts can also be reached for expression of any concern or observation: 090-865-00545 or 080-383-62072. Our website is www.education.kdsg.gov.ng. Our email education@kdsg.gov.ng or education.kdsg@gmail.com. Our YouTube channel, Ministry of Education, Kaduna State. Our Twitter handle @Kaduna_MOE. Or our Facebook page, Ministry of Education, Kaduna State. Stay safe, stay at home, and learn well. Thank you, happy listening, and happy viewing.
Hi, my student at home. You are welcome to Kaduna State Ministry of Education Radio Television e-learning program. My name is Williams Ishaku. This morning, we will be looking at chemistry under the topic nuclear chemistry. This is a continuation of our previous lessons. This is TAC Nuclear Chemistry 2. You will recall that in our previous lessons, we discussed about the radioactivity, the definition and other aspects of the nuclear chemistry. Today, we intend to continue with the remaining aspect of it. Not to take much of your time, let us, under this, we are going to see the instrument used in detecting radiations, the types of artificial transmutation. Under that, we are going to see nuclear fission and nuclear fusion, half-life in nuclear processes, the use of radioactivity and nuclear reaction. We are also going to see, lastly, health hazards in radioactivity. Now, I believe you are going to sit down and then learn, as that is our priority in life. To start with, we are going to see the instrument that we use whenever we are talking about how to detect whether a substance is radioactive or not. You will recall we made mention the other day that each time radioactivity is taking place, there are 3 particles that can be emitted by this radioactive element. They are alpha, beta, and gamma. As such, we are going to see how do we detect the presence of these 3 radioactive particles. To do that, we make use of this following instrument. The first one is called the Geiger Muller counter. It is used in detecting. We also have the second one, the Wilson diffusion cloud chamber. The third one, we have the scintillation counter. The fourth one, we have the photographic plates. And the fifth one, we have the fluorescent screen coated with zinc sulfide. It fluoresces means that it glows. By this instrument, we can detect the presence of alpha, beta, and gamma, the 3 particles that can be radiated by what? A radioactive element easily. Next to that, we are going to see each time radioactivity is taking place, we all know that it can either be artificial or natural. The artificial radioactivity was proposed in 1919 by Ernest Rutherford. And by this, we describe such type of artificial transmutation, where we deal with the two aspects of it. We have the nuclear fission and nuclear fusion. Don't get the name confused. The F of the other one is I, which means fusion, and the other one is fusion. Now let us see what is nuclear fusion and what is nuclear fusion. Let's start with the nuclear fission, the one with the I. This is the breaking down of heavy radioisotopes into two or more smaller nuclei of almost equal sizes with the release of high amount of energy. It is usually a chain reaction. A typical example of this type of reaction, we can use uranium. When we have uranium-235 with atomic number 92, if you bombard the nucleus of uranium with a fast-moving neutron, it is going to disintegrate, or in other words, break, to give us strontium-90 with atomic mass 90 and atomic number 38, plus xenon with atomic mass 144 and atomic number 54. And neutron is also released with the release of high amount of heat energy. This heat energy that is being released at the cause of this nuclear reaction can be trapped and put into other uses that we usually celebrate countries that have 100 years of uninterrupted power supply. They use that as nuclear plant to generate electricity. And the next type of nuclear transmutation that we are talking about is nuclear fusion. This is a type of nuclear transmutation that involves the combination of two or more smaller light nuclide to produce a single heavy nucleus with the release of high amount of energy. Example of this type of nuclear fusion, you can see we have two isotopes of hydrogen. One is H2 with H with atomic mass 2 and atomic number 1. It is called deuterium in chemistry. And the other one is H with atomic mass 3 and atomic number 1. We call it tritium. It is going, they will combine together and then give us a larger nuclei, like one of them is helium with atomic mass 4 and atomic number 2. Neutron molecule is also there with the release of heat energy. Like I said, we always trap this heat energy in making so many things. Like this one, this is a typical example of what they use in making what we call hydrogen bomb. Hydrogen bomb that is used in warfare. However, let us also see, whenever we are talking about this nuclear reaction, whether fusion or fission, we want to study, each time we want to study their rate of reaction, we make use of what we call half-life. This nuclear molecule disintegrate, they break at a particular point. And in chemistry, we describe that as half-life. What is half-life? Half-life we usually represent half-life using what we call T-half. Some use capital T, some we use small t with the half. Is it of a radioactive isotope? Is the time taken for a radioactive element to decay half of its original total mass or value? By this, mathematically, this can be represented in this equation, as you can see above. T-half, that is the half-life, is equal to 0.639 all over K, where K is the decay rate constant. Every substance you see in this planet Earth has its own decay rate constant. By this, we can know, if we know the standard of that decay rate constant of a particular particle, we will now plot it under that equation, and then we'll detect the half-life. That will now tell us the number of years the particular article has spent in the planet Earth. Again, this half-life can be used to study, like I mentioned earlier, we use the half-life to study the radioactive decay rate. However, they may ask you this kind of question. There's this question that is always common in WAEC or NECO or any other standard examination. They can put it in this way. What is the half-life of so element? Or they can put it in this way. The half-life of manganese 5621 is 1.2 times 10 to the power of 3 seconds. What do you understand by this statement? It simply means it is going to take manganese 5621 1.2 times 10 to the power of 3 seconds to decay half of its original total mass or value. So this half-life is very, very important. It can be represented graphically, as you can see from the table above. Imagine that I'm an element. I can, at a particular year, half of my mass will break. After another year again, half of my mass will break. You can see at the first half-life of the other element, you can see the concentration at the vertical axis and the time in seconds at the what? At the horizontal axis. At 0.8, the first half-life, we have the first half-life. At the second, at 0.4, half of it, we have the second half-life. And the third one at 0.1, 2, we have this, at 0.1, we have the other half-life. By this nuclear transmutation will always occur. They break, they don't remain. They are always breaking intermittently. However, in each time we are talking about half-life, we do calculate the half-life of different substances in which we use them as chemists to predict the number of years of a particular particle or element. To do that, we have so many formulas that can help us. We have up to about 6. But for the purpose of this lecture, I'm going to give you 1 or 2. I've given you one already. That one that we stated, the other one we said is T half is equals to 0.319 all over K. You can use that one to determine the half-life. Another one that we are going to use here is the one you can see above. Is stating that we have capital T is equal to small t all over log base 2 capital R, which is the same thing as small t times log raised to the power of 2 all over log raised to the power of capital R, where R is equals to 2 raised to the power of n. That n is telling you the number of the half-life. Is that clear? We also have your n, that is, as you can see above, n1, that is the original mass, and n2 is the final mass. In other words, you are going to get your number of disintegration, which is n, which is equals to small t all over capital T. These are the meaning of these parameters that we are using. T half-life of a radioactive element. Capital T stands for half-life of a radioactive element. Small t stands for time taken for the radioactive element to decay, while the N1 is the initial mass. If you don't want to call it initial mass, you can call it the radioactive, you can call it the number of atoms present. We also have the N2, which is equal to the mass of the final, number of atoms remaining on decay. Our capital R is the disintegrating ratio. We always relate that one to carry out our calculations. Let us see one example that will help us. This is a conventional example that will help us each time we want to calculate the half-life of a radioactive element. The question is there. The half-life of a radioactive material is 6 hours. What quantity of 1 gram of the material would decay in 24 hours? The method, this is the conventional method that we are used to. Is that clear? You are going to divide it, since it is 6 and the hour is what, 24. If you divide 6 divided by 24, it's going to give you how many times? 4. That shows you will be multiplying each and every one by what? Half, to get the value that will disintegrate at the end of the day. For the first one, there, after 6 hours, half kilogram decay and 1 kilogram A half kilogram will decay to give us half of a kilogram. After the next 6 hours, that shows the disintegration will be taking place after every 6 hours. Another one, half times half kilogram, would decay to give you the remaining mass that will be remaining will be equals to 1 all over 4. If you multiply again after the next 6 hours, half times 1 all over 4 kg decay, and 1 all over 8 kilogram remain. After the next 6 hours again, half times 1 all over 8 kilogram decay, and 1 all over 16 kilogram remains. Therefore, the material that will decay finally will be, you subtract, since it is 1 gram, you are going to subtract it minus 1 all over 16, since it is 4 times. Then you are going to get the remaining mass will be 15 all over 16 gram. So this is the conventional method. Another example of half-life that they can also ask you to calculate is the question you can see in example 2. That one we have, in 24 days, a radioactive isotope decrease in mass from 64 to 2 grams. What is the half-life of the radioactive material? You can see the solution below. Please, can we see the solution below? You can see the solution. You write your solution. You collect your data. For the decay time is small t, which is equal to what? 24 days. The half-life, like I said earlier, we always represent the half-life using capital T. We also have our initial mass. From the question, our initial mass N1 is 64. The final mass remaining is N2, is represented as N2, which is equal to what? 2 grams. The decay ratio that we always call it, the first thing to do here is to calculate your decay ratio. And then you substitute it from the formula, and then you get your half-life. What is your decay ratio? Capital R is equals to N1 all over N2. What is our N1? Our N1 from the question is 64, where our N2 is 2. If you divide 64 by 2, you are going to get 32. That will give you the decay, the decay ratio constant of the represented as capital R. Okay. Then you will now see the T half, which is equals to, you will now substitute it from the formula. T is equals to small t all over log base 2 raised to the power of capital R, which is equals to 24 log base 2 32. Log base 2 32 is the same thing as 5. So therefore, if you say 24 divided by 5, you are going to get 4.8 days. Now, here we go, my student. These radioisotopes are very, very important to us. We are going to see their uses. They are so important that we cannot even exhaust their importance. The first one there is that, like I mentioned earlier, you hear countries like developed part of the world celebrating 100 years of uninterrupted power supply. What are they using? They are using these radioisotopes, especially uranium. It is capable of disintegrating to generate high amount of energy that is trapped to supply electricity. The second one, it is used in making hydrogen bomb, from the illustration we gave you under nuclear fusion, which is used in warfare. The third one is, it is used in radioactive dating, carbon dating. We use this one, some of the unstable isotopes like carbon-14, to determine if we can determine their half-life. Then we have their decay rate from that other formula. Then we calculate and know exactly the number of years a particular article is. Again, when we use it in gauging thickness, like you will recall in our previous lessons, we made mention that these radioactive particles are capable of penetrating into certain material, and their level of penetration depend. Okay. Their level of penetration depend on the level of a material thickness. So we use this one to ascertain the thickness of a particular material. We use radioactive isotope also to determine the reaction mechanism of a particular reaction, as you can see in the case of a half-life, a radioactive particle. We also use it as a stressor to detect leakages in pipelines and in chemical reaction. There are certain particles that we can use them to detect the stressing ability of a particular particle in a particular reaction. Through a particular reaction that will take place, we'll be able to decode that there is leakages in this pipe. In the area of medicine, we use it in curing malignant growth of cancer. We use cobalt-60 and iodine-131 to cure such sicknesses. We induce them, ionize them into the position of the virus, and then it will now destroy it. In the production of new element, you will recall that in our previous knowledge about periodic table, we made mention that the element in group F, most of them are artificial elements created by this. In agriculture, for making insecticide, fertilizer, and so on and so forth. These are some of the uses of this radioisotope. My student, don't forget, these radioactive isotopes can also be in as much as they are useful, they can also be harmful to us. If you continue to expose yourself to them, at a particular point in time, you are coming in to get yourself infected with certain diseases that can lead to death. Common one among them is what we call genetic mutation, a situation whereby the offspring does not resemble its own parent. It can occur. We have a lot of chromosomal distortion as a result of the position of the DNA being affected by this radioactive element. It can lead to cancerous diseases such as leukemia, which is cancer of the blood, another cancer. So we are not supposed to be exposing ourselves under these radioisotopes. That is why each time you see people that are working with this dangerous radioactive element, they always protect themselves. They wear protective clothes to protect themselves. Again, these radioactive isotopes can also lead to death, nausea, and other things. So please, my student, whenever you are talking about radioactive element, you need to stay safe so that you protect yourself against these dangerous diseases. My student, I believe you have learned. Time will not permit me to go into details the way it is. But permit me to invite my able colleague, Mr. Philip Maman, to come forward for a recap of what we have just discussed. Stay safe and remain blessed. Thank you. See you another time.
You're welcome, my wonderful students. I'm sure you have learned from the beautiful presentation by my noble colleagues, Mr. Williams Ishaku. He tried to dive into the issue of nuclear chemistry. In our previous lesson, we have told you that nuclear chemistry has to do with the nucleus, involving the proton and the neutron. And we say that there are differences between ordinary chemical reactions and nuclear reaction. Some of those things we have seen today, as we have seen artificial transmutation, which is the artificial aspect of nuclear chemistry. And we say there are two basic reactions involved in that. The first one is nuclear fission. When you say fission, it means to split. So when we say nuclear fission, it means when a heavy nucleus is splitted into two or more smaller nuclei of comparable sizes. That's what we refer to as nuclear fission. Now, it's important that in your definition, you note that the two or more daughter nuclei will be of comparable sizes of all or almost equal sizes. But when we say fusion, it means to bring together. So when you fuse, it means that when two light nuclei are joined together to form a heavy nucleus. Now, the both nuclear fission and nuclear fission are accompanied by a release of enormous amount of energy. Mr. Williams also talked about half-life in a nuclear process. Now, like he said in his definition, half-life is the total time taken for a radioactive substance to decay to half its original size, meaning that if it were originally 10 grams, by the time it decays to 5 grams, it becomes the half. The time taken for it to decay to 5 grams is what we refer to as half-life. He was able to illustrate it using your graph, and mostly archaeologists use it to carbon date. For instance, you find out that after a long period of time, if a particular environment has been deserted, once archaeologists go there, they dig the remains. I mean, maybe spoons, pots, or those things that people that lived there used. And they will find out the half-life of the material. And they're able to tell you that, okay, people lived here so number of years ago. So it's called carbon dating. Now, he talked about the uses of radioactivity, which are quite enormous. But I want to draw your attention that when you want to give uses for radioactivity, you have to be specific because there are so many radioactive substances. For instance, he says that X-ray is used for medical purposes. Now, one of the uses of X-rays is to kill cancer growth, or is used to take photograph of internal materials, and so on and so forth. Iodine is used for treatment of thyroid gland diseases, and so on and so forth. So he has mentioned the health hazard of radioactivity. As you can see, it's nuclear chemistry, the discovery of nuclear chemistry that brought to an end the Second World War, as the impact was seen in Hiroshima, Nagasaki. And up to today, the Asian people are still suffering from the effect of this dangerous emission. Now, we'll go to the assignments, and the assignment goes to us. It says, what is half-life? What is half-life? The second one says, state two differences between nuclear fusion and nuclear fission. State two differences between nuclear fusion and nuclear fission. Number 2 says, distinguish between chemical reactions and nuclear reactions. Distinguish between chemical reactions and nuclear reaction. Number 3 says, name two equipments used in dictating radioactive emission. Name two equipments used in dictating radioactive emissions. Number 3, balance the following nuclear reaction: uranium-238, 92, to thorium-234, 90, and the other one there, X. X is an element. You can only identify it if you're able to balance the equation. Then, of course, says aluminium-2813 plus giving you silicon-2814 plus Q. You'll be able to tell us what Q is, an atomic number as well as atomic mass of Q. Then the last one says nitrogen-14.7 plus helium-4.2 to give you oxygen-19.8 and Y. You should be able to tell us what Y is. Then the last one says give 3 applications of radioactivity. Application is the same thing as uses, please. So take note of that. My good students, when you are confronted with a question in an examination like WAEC, and the question says, what is? Before you know the extent of write-up to do, try to find out how many marks are attached to that question. If they say, what is, and the mark is only 2, just define and stop there. But if the mark is more than 2, it means you can go further and do other explanation. You can go further to see what we have said from these reference materials: Understanding Chemistry by Godwin O. Ojokuku, and Senior Secondary School Chemistry by S.T. Baja et al. It means there are other authors associated with this. As usual, you can contact us using our WhatsApp numbers. The first number here is Mr. Williams Ishaku, your first presenter. His number is 081 60 67 0920. 081 60 67 0920. My number, Mr. Philip Mamman, is 080 26 59 8861. 080 26 59 8861. And of course, Ibrahim Umar, 070 3620 2842. 070 3620 2842. Keep reading your books, stay safe, stay at home, obey all the rules and guidelines by NCDC and the state government. God bless you.